Hello, my name is Eric Shook, and I'm an associate professor at the University of Minnesota. This talk will discuss how we can create the next generation scalable geospatial processing architecture. We live in a big world filled with major societal and environmental challenges. GeoConvergence envisions a world where we can combine numerous geospatial approaches to examine, understand, and overcome these grand challenges. But to realize this vision will require solving a foundational problem, which is to create a geocomputational architecture that can enable geoconvergence. In this talk, we will discuss clear ways forward in creating potential solutions, collaborations, and milestones for realizing the next generation scalable geospatial processing architecture. A clear challenge is data. We now live in a cyber landscape filled with data streams, data lakes, mountains of location information, which has created a data tsunami that our existing solutions cannot hope to handle. This problem is beautifully articulated in the Trillion Pixel Challenge workshop hosted by Oak Ridge National Lab. The Trillion Pixel Challenge recognizes that constellation satellites are now capable of taking a picture of every place on the Earth's surface every single day at high resolution, creating trillions of pixels. The challenge is to process, analyze, and make sense of these pixels before the next trillion pixels comes in 24 hours. Dr. May Casterline and I co-organized a session focused on creating a scalable geospatial processing architecture for GeoAI. We had a diverse group of panelists from academia, national labs, and the commercial sector who provided their views on the opportunities and challenges we're facing. In our panel, we encouraged our panelists and audience members to think bigger. In the panel, we discussed the challenges of pipelines using state-of-the-art technologies which aim to transform societal and environmental processes into computational processes as they go down through the software and hardware stacks. Our panelists raised a number of interesting points, and I highlight a few key points here, and the full report will be available in June. In summary, we can say that we have built many complex systems, but many of our solutions have been stuck in silos, and the state of the art does not fit our needs. Following the panel, ongoing research, and collaborations, I have come to believe that we have been working backwards. Rather than trying to fit the world out there into the computers we have today, we should instead build a geocomputational system from the bottom up that rises to meet our needs to support and combine all of these geospatial approaches to achieve geoconvergence. Such a system could become the community-owned innovation platform for GIScience called for by Mark Geoghegan in a 2018 article. It also could help address the needs of the GIScience community who report that geospatial software inadequacies have limited their work, published in a 2020 article by Rebecca Vanderwall and collaborators. This platform would need to overcome several challenges identified in our workshop panel, including the movement of data from bits on storage systems to the chips on compute nodes, with the goal of maximizing the computational scale while minimizing the movement of data. What also emerged is the need for open, ethical, and scalable geospatial benchmarks. Such benchmarks can help the commercial sector advertise their strengths and contributions and help scientists measure progress. Benchmarks can also play a role in guiding design and development decisions toward improving scalability and performance. Evidence of this can be seen in the top 500 list for supercomputers published every 6 months for decades using the LINPACK benchmark. We can build on existing benchmarks in raster big data, computer vision, high-performance computing, and global challenges. Such benchmarks and challenges can create healthy competition to advance research and development. In summary, we lack a geospatial architecture to enable geoconvergence. With multi-institution and multidisciplinary collaboration, we believe we can realize the next generation scalable geospatial processing architecture and a set of benchmarks to measure progress and to guide decisions. I would like to thank the organizers of the GeoConvergence workshop, Dr. May Casterline, Dr. David Haynes, the National Science Foundation, as well as the other organizers and supporters of this research, including many great students who I've collaborated with.